Imagine rolling a ball down a smooth bowl. It races down quickly, but near the bottom it starts zigzagging, taking forever to settle. Why does it slow down? We saw gradient descent zigzag. Second-order optimization fixes this by not just seeing the slope, but also how the slope itself is curving. It's like knowing the shape of the whole bowl, not just the tilt under your feet. The tool for this is called the Hessian. The name comes from the 19th century mathematician Ludwig Otto Hesse. It's a table of second derivatives that captures the curvature in every direction at once. We just saw the Hessian captures curvature. Here's why that matters. A first-order method only sees the local slope. On a curved surface like this narrow valley, the slope points sideways, causing a zigzag that never goes straight to the bottom. The Hessian measures how quickly the slope itself changes. By using this curvature, we can predict where the slope will become. We just saw why curvature matters. Now, let's step back. Optimization is simply a hiker trying to find the lowest valley floor. The height of the land is our objective function, and the hiker's map coordinates are the parameters we can change. Our hiker is blindfolded. She can only feel the ground slope under her feet. She takes a step downhill, then rechecks the slope. This iterative search repeats until she reaches a flat basin, a minimum, where the slope is 0. A real landscape has many dips. A local minimum is the lowest point in your immediate neighborhood, but the global. Our hiker just felt the local slope underfoot. Now, imagine that slope as an arrow pointing straight uphill. That's the gradient. It always points in the direction of steepest ascent, cutting directly across the contour lines. To descend, the hiker takes a small step in the exact opposite direction of that arrow. The size of this step is the learning rate. A tiny step is safe but slow, a giant step might leap right over the valley. This method is called first order because it only looks at the slope, the first derivative. It's completely blind to the landscape's curvature. That's why it zigzags in valleys, a problem we'll fix next using second-order information. We just followed the slope downhill. But in a narrow, tilted valley, the slope points mostly across the channel, not along it. So we overshoot, correct back, and zigzag instead of gliding straight to the bottom. On a flat plateau, the slope is almost 0. The hiker takes tiny, timid steps and barely moves, even though the true minimum is just ahead. The slope alone gives no clue how far to go. The missing piece is curvature, how fast the slope itself is changing. A sharp curve means the slope flips quickly, so take a small step. A gentle curve, we just saw how following the slope alone can zigzag. Now let's look at the bowl itself. A simple parabola, y equals x squared, reveals the missing piece. Watch the tangent line as we slide along. Near the bottom, the slope changes gently, that's low curvature. Further out, the slope tilts rapidly, high curvature. Curvature is simply how fast the slope itself is changing. The slope of a curve is its first derivative. The rate at which that slope changes, its curvature, is the second derivative. For our parabola, that curvature is a constant too, meaning the bowl has the same tightness everywhere. We just saw curvature on a single curve. Now imagine a 3D bowl. The slope changes differently depending on which direction you face. The Hessian captures all these curvatures at once. The Hessian is a square table. Each entry is a second derivative. The diagonal tells you how the slope changes along one axis. The off-diagonals tell you how changing one parameter twists the slope of another. A contour map shows rings of equal height. Where the rings bunch tightly together, the bowl is steep and curvature is high. Where they spread out, the slope changes slowly. We just mapped the curvature with the Hessian. Now, Let's use both the slope and curvature to build a perfect little quadratic bowl that matches the landscape exactly at our feet. Because this bowl is just a simple quadratic, we can solve for its very bottom in one go. We jump straight there, no zigzagging, no guessing step sizes. The rule is simple: subtract the slope, scaled by the inverse of the curvature. If the bowl is sharply curved, we take a tiny step. We just saw Newton's perfect jump land exactly at the minimum of a simple bowl. But real-world lost landscapes have bumps and twists. Newton's formula still assumes it's a perfect bowl, so it can leap far past the true minimum into worse territory. Even worse, if the landscape curves downward, negative second derivative, Newton's jump points uphill. It treats the upside-down bowl as if it were right side up, sending you toward a maximum, not a minimum. To fix this, we add a damping factor, a penalty on large steps. This shrinks the Newton jump, blending it with a cautious gradient step. When the bowl looks trustworthy, we step boldly; when it doesn't, we inch forward like first-order methods. We just saw damping makes Newton's jump safe. But there's a bigger catch. Modern neural nets easily have 1,000,000 parameters. The Hessian must store how every parameter curves with every other parameter. 1,000,000,000,000 numbers. Just storing that matrix would take around 4 terabytes of memory. And remember, the Newton step needs the inverse of this giant, a computation that's completely out of reach. So the exact Newton step is a beautiful idea that's computationally impossible for real-world deep learning. This forces us to find clever ways to approximate the curvature without building the we just hit a wall. Computing the full Hessian is too slow. But imagine a blind hiker. She can't see the whole valley, yet she can map the shape by feeling how the ground tilts differently with each step. That's the key idea. Curvature is just how much the slope changes. If we compare the gradient before and after a step, the difference tells us how curved that direction was. We can use this to build an approximate Hessian, step by step. We start with a simple guess, a flat landscape. After each step, the BFGS formula updates our curvature map using only the gradient change we just measured. The map gets sharper, like a blind person gradually building a mental model of the room. We just saw BFGS build an approximate Hessian. But storing that full matrix is like carrying a giant map. LBFGS instead keeps a short diary of the last few steps and slope changes, just enough to reconstruct the curvature. Each diary entry is a pair, the step we took, and how the slope changed because of it. From these few pairs, LBFGS can cleverly reconstruct the local curvature without ever building the full matrix. Using just this compressed history, LBFGS computes a direction that mimics a Newton step, scaling the gradient by the local curvature, but with memory that stays tiny even for millions. We just saw how LBFGS cleverly approximates the Hessian. But even a perfect jump can lead to zigzagging, where each new step partially ruins the work of the last. Instead of computing curvature, conjugate gradient enforces a simple rule: each new search direction must be conjugate to all previous ones. This means it won't interfere with the progress already made. Picture a long, tilted valley. The first step takes you straight to the bottom. The next, conjugate direction turns you along the floor, never climbing back up the walls. For an n-parameter problem, we just saw conjugate gradient cleverly avoid storing big matrices. Now let's see where these second-order methods shine, any field needing exact answers from small, precise models. Each second-order step costs more compute but makes far more progress. When your model has millions of parameters, that cost becomes impossible, so deep learning sticks with cheap first-order steps. So the choice is clear: when every parameter must be exactly right, physics, statistics, engineering pay for second order. When scale dwarfs precision, survive with first order. Next, we'll wrap up. We started with a hiker feeling only the local slope. That's gradient descent, slow and easily fooled by flat plateaus. Curvature revealed the bowl's true shape, and the Hessian gave us a complete map of every valley and ridge. The Newton step offered a perfect jump straight to the minimum, but computing the full Hessian was too costly. So we built clever shortcuts, BFGS, LBFGS, and conjugate gradient, each approximating curvature without the heavy price. Here's the one-sentence takeaway. Second-order optimization uses curvature to choose both a smarter direction and a smarter step size, and the art is approximating that curvature cheaply enough to make it practical. Remember the ball in the bowl? Let's solve that puzzle. We'll place the ball at the rim and watch it roll down with real numbers. A first-order method only sees the local slope. The slope is much steeper across the narrow valley than along it, so each step zigzags instead of heading straight to the center. Now use the Hessian, it sees the bowl's true shape. Multiplying the gradient by the inverse Hessian perfectly compensates for the narrow valley, so one step lands exactly at the bottom. We just solved the zigzag puzzle. So here's the master rule: always think about curvature. Before you take a step, ask if the valley is curved. That single question is what separates second-order methods from blind gradient descent. The biggest mistake is treating the Hessian as perfect truth. Remember, it's just a local, quadratic guess, like using a flat map for a round Earth. Real-world lost landscapes have cliffs and twists far from your current point. To lock this in, think of Newton's method as a new turn. A first-order step runs straight downhill. A second-order step turns to follow the valley's curve, aiming directly for the bottom. Now, prove it to yourself. Take this simple valley function.